Hello, everyone. Welcome to the Interpretable Natural Language Processing. This is talk 0. We're starting counting from 0. And this is a short introduction to Interpretable NLP. And in this slide, we will briefly go through some motivations for studying the Interpretable NLP. And basically, what is this about and why we're doing this. So currently, deep neural network-based NLP systems are really good. One of the most popular benchmarks that are used to test the performances of natural language processing systems is called SuperGLUE. This is an updated version from the previous GLUE benchmark. And in this SuperGLUE benchmark, they used a series of harder tasks. We'll go through some of the examples of the tasks in the future slides. And at this slide, we will see that the human baseline is not ranked the first. Not only that, it's around 89.8%. There are two submissions by Google Brain and Microsoft respectively that are achieving a score that's even higher than the human baseline. And following the human baseline, there are several other teams that achieves the performance that are really close to that human performance. So what human baseline means is that they find a group of humans and do these tasks, and then they've observed that the humans that they find to do this task did that a little bit differently from the original humans that they recruited to label these data sets. So if the machine performances are very close to the human baselines, that means that the difference between the machines and the labelers are comparable to the differences between humans, human participants and the human labelers. So that is a very strong evidence that the current deep neural network-based NLP systems are close to as good as they possibly can be, because one of the original goals of NLP is to let the machines process natural languages close to humans, similar to the way that we humans are processing the languages. And currently, apparently, they are doing that, and sometimes they are doing that better. BlueQ dataset is an example of the SuperGLUE benchmarks. In this dataset, the models are required to check the facts in reading comprehension. For example, that in this dataset instance, we present this piece of text to the model. Epsom railway station serves the town of Epsom in Surrey. It's located in some locations. It's not in the London Oyster card zone, unlike or something. And question, can you use the Oyster card at Epsom station? So the answer is no, because it's not in the card zone. And in order to give a definitive no answer, the machine has to first locate that this station is not in the card zone, and it has to figure out that the it here refers to the Epsom railway station. So this is a pretty complicated task, but the best DNA models can reach above 90% of accuracy. Here's another task, is the IMDb classification. So this requires understanding the sentiments that are contained in the text. So IMDb contains a bunch of movie reviews, and when the users submit the movie reviews, they write some text that explains why they like it or don't like it, and they also give some scores. For example, if they like the movie really much, they will give 5 stars. Otherwise, they might explain some reasons for why they took off some scores, some stars out of the marking systems. And this is, for example, in this task, in this text example, they said they've just finished listening to the director's commentary for this film, and I think the one big thing I got from it is that I agree with that is this film is completely subjective. So any review or attempt at contemplating a set of comments about it is really about the North's character, actually. If you feel as he did that the movie does not work, then you are saying the horror does not work. And to be frank, you might be right. Howard's reasoning and personality really wouldn't stand up to professional mental treatment and analysis. But hey, that's the nature of people, Andrew. So this review says that the comments or reviews about the movie is not about the movie. It's actually about the character that's acted in the movie. So one interpretation is that this movie faithfully conveys the character of that person, Howard, and this is a pretty positive interpretation on if we look from this perspective, but there might be other alternative interpretations, because this text does not directly say whether it's a positive or a negative test. And regardless, this in the data set, this sample is labeled positive, and the best deep neural networks model can reach above 96% accuracy on the IMDb classification tasks. And translation in compared to the previous classification task is even more complicated. This requires the models to learn to know both the grammar and the semantics. So human needs years to study this. There's in each language, there are a set of grammatical rules, and there's some ways to map the semantics to the apparent tokens and lexicons in the language, and there are some grammars to associate them together. But the deep neural networks can be used to help us study the foreign languages. For example, this is a screenshot taken from a website called DeepL, and if we input, for example, English and translate into French, then this website can even give us several alternatives for the translation. For example, what's the weather like can be translated into quel est le temps, and quel est le temps qu'il fait, and que temps fallait. And I think there are mature translation systems between very popular languages like English, French, German, Chinese, and Spanish, many other languages. Like I think more than 100 languages are supported by Google Translation. So the best deep neural networks models apparently have learned a lot of this grammar and semantics well, and they are doing that to the extent that they can help us study foreign languages. So the deep neural networks are so good, but we can sort of summarize the sentiment using this meme. It works. I don't know why. So unless we figure out why they are working or why they do not work, there's no way that people can eventually trust them. So recently, the language models have become larger. This is a screenshot from the stochastic parrots paper. And in 2019, when people trained BERT, DistilBERT, Albert, Ernie paper, the models, they're using the book corpus and Wikipedia, and the combined dataset size was around 16 gigabytes. But later, people found out that if we would use larger dataset, it might result in better models. So Crossanet and Roberta and Megatron LLM was using between 100 and 200 gigabytes. And in 2020, Google and OpenAI pushed that to sort of a limit. Google pushed sort of dumped 745 gigabytes of data to train a T5, right? And OpenAI used 570 gigabytes of data to train GPT-3. So the larger the data set they are using, and of course the more parameters they're using, the models have higher potentials to reach lower validation loss, which is the larger models might lead to higher performances. But on the other hand, this requires more computation. This requires much more computation than almost anyone outside Google, OpenAI, or Microsoft can afford. In 2019, training Elmo only takes around 336 hours on 3 cards, and this is around $1,000 on the cloud computing engine, and similar to BirdBase. So if we're using TPU, which is around 100 to 1,000 times as fast as a P100 card, then the cloud computing cost is manageable. But the GPT-3 is definitely not like as affordable as the previous generation models. So according to the estimation from Lambda Labs, which is themselves a provider for cloud computing engines, that they estimated that if we're using 8 cards using the V100, which is the cheapest version of the cards on the Lambda Labs, they will require around 44 years to to train a GPT-3, and they would take about $4.6 million. Actually, in the GPT-3 paper, the authors said that they use around 10 times as much as that, and because the cost was so large, even if they found some bugs in generating the data, they were not able to retrain this model because they would otherwise cost too much money. Another concern is that the large deep neural network models might not be as good as the accuracies are showing. Ribeiro et al. In 2020 used a tool called Checklist to show that we can break many state-of-the-art, even commercial classifiers with some simple tests. Let's look at some examples of the categories of the adversarial tests that they built that they show to be able to break many state-of-the-art models. The first one is that negation of negative at the end should be positive or neutral. So if you have a negative sentence, for example, I thought the plane would be awful, and you append a negation at the end, but it wasn't, then the whole sentence should become either positive or neutral. It turns out that the popular models from Microsoft, Google, Amazon, and or the state-of-the-art model, like BirdBase, for example, they almost failed completely at these categories. The error rate goes to like 90% or even 100%. Similar things happen for the negative neutral should still be neutral category. So this aircraft is not private. So the label should be neutral, but but many of the models are predicting either positive or negative of this sentence. There are several additional categories that Checklist found that could break the state-of-the-art deep learning models. For example, the author's sentiment should be more important than others. some people hate you, but I think you're exceptional. So the overall sentiment of this sentence should be dependent on the authors more than dependent on the others. So so this is different from the like majority voting. For example, if we're counting the majority voting, then probably the people that hate you would be more than the people who think you are exceptional. But the author sentiment should be more important than everyone else. So this sentence is overall positive. But there are the like state-of-the-art and commercial models have a high chance to think that these categories of sentence are not positive. And when we another category is that if we append no to a question, then it's like we ask ourselves a question and then we answer it ourselves with no, then the overall label should be negative. But it seems like many of the commercial models focus a lot on the previous part instead of the overall sentence. So when they look at do I think this pilot was fantastic, they would probably just output a large probability weight that outweigh the appended part. So as we can see, Microsoft gives 96.8% of error rates on this category. So although the accuracies are high, there are still a lot of the dark corners that are not covered by the deep neural network models. So before deploying to the real world, we should be really careful about these dark corners. But another thing is that the high accuracy themselves should they themselves could be spurious. So the models can be right, but they are right for the wrong reasons. So for example, in a Quora data pair classification task, we are provided with two sentences, and the model is trying to classify whether these two sentences are from a similar question. For example, what can make physics easy to learn? How can you make physics easy to learn? These two are almost the same questions. The labels should be true, but the reason is that they have very similar meanings. But the model might be making this shortcut that they classify true not because they have similar meanings, but because they both contain can, to, and question mark. Similar things could happen on a data set called multi-natural language inference. You have access to the facts. The facts are accessible to you. So these two sentences entail each other. So the label should be entailment. But the models might not be making the positive classification because of this positive reason. Instead, that they might be giving the entailment label because they both contain the, to, and you. So these models can be right, but for the wrong reasons. They might look appealing in the classification data sets, but when we move out of the data set and move into the real world, these shortcuts, could they generalize? I'm very skeptical about whether they can generalize. Another argument recently is that the goodness of good performance is itself debatable. Calvin and Dan wrote a paper in 2020 saying that utility is in the eye of the user. So the utility is a broader terms that includes accuracy, and if the utility is is high for doing something, then it's that there are a lot of benefits in doing so. So for large firms like OpenAI and Google, high performance, for example, high accuracy contains a lot of utility. But for Qualcomm, they would prefer small and fast models, even if the accuracies are like 1 or 2% lower than the state of the art. And for NVIDIA, probably parallelizable models are better. So in this sense, they will definitely prefer transformers than LSTMs because transformers are much easier to parallelize. So we can utilize the powerful GPUs that they are building. And for investment banks, they will probably prefer the robust and reliable models. In some sense, linear regressions might even be better than the neural network classifiers because with the linear regressions, although they might have they might have lower accuracy in predicting whether the stock price will rise or drop, they will produce less surprisal, and the results are less surprising than those provided by the deep neural networks. So if we're doing the trading, then probably surprise. Then we probably want to avoid being too surprised, unless we are well prepared and be ready to take advantage of this surprisal. So different people would want different performance, and the good performance is like it really depends on the users. We can't just say that the high accuracies are good or something like that. And leaderboard chasing is sort of it's definitely a good thing, but it's not good for people for people who want to apply the deep neural networks onto different categories. So this paper proposes to set up different categories of leaderboards, so that when people are chasing the leaderboards, they can do that on more than the accuracy themselves. For example, they can optimize for the speed or parallelizability or the robustness. And how about deployment? Deployment means interacting with real humans, and this is really complicated. The Hitchcock experiment is an example of showing how complicated it is to interact with real people. And in 2013, from 2013 to 2015, a bunch of Canadian researchers built a huge bot that could make dialogues with real humans, and they put this robot onto the street, and the robot waits for the drivers to pick them up and does some conversations with them, and then drop them off at another station. And they are for as long as 2 years, the Hitchbot was successful in traveling for a long distance. And sometime in 2015, when it was trying to travel across, I think it was Philadelphia, it was disconnected from the internet. And when people found that again, it was broken. So it might be that some drivers dropped it off accidentally, or someone just, instead of stopping and giving the Hitchbot a ride, is ended up hitting the robot and it broke it. And the deployment should be fair, accountable, and transparent. So in 2017, the European Union has enforce the GDPR, the General Data Protection Regulation. So the end goal is to protect the data that is associated to the daily users. So everyone has some data that needs to be protected. I remember there was a famous argument about the data privacy. So even if the author was claiming that privacy was not about having some secret. It was about having something to protect, and everyone has something that they want to protect. He proceeded with asking the audience that if there is someone who really thinks there's no privacy and there's nothing that he needs to be protecting, and if not, could you share the bank account number and then passwords? So at least the bank account number and passwords are something that everyone wants to protect. And actually in the real world, there are much more than those data. And similarly, deep neural network models should be accountable and transparent. And if you are using a black box model, for example, if you are talking to a voice assistant, and then the voice assistant remembers your commands and your data and reviews to other people, which we already saw that the news had, I think it's last year. This would be a very bad thing, and this would be very detrimental to the credibility of this voice assistant. And there is a huge bunch of argument about the fairness of the models. So if the model has intrinsic bias towards a particular group of people, then this model might be amplifying instead of healing the society and the users. So when deploying the models, we should consider both the models itself in the task and its externality. So by doing this task in some specific ways, the models might be either positively or negatively affecting the society. And those broader impacts are usually not discussed within the academic context. And deployment should, and even before the deployment, in designing the models and building the systems, we should start to take this into considerations. And summary, why interpretable natural language processing? So we want to build NLP models with high performances, but the high performance itself is debatable. We should explain the goodness of this good performance, like whether it's high accuracy or whether it's avoiding some dark corners and let the models be more robust against any types of input, or whether it's we want to let the models be as simple as possible and avoid giving us too much surprises. And these are all relevant to interpretable natural language processing. So we want the NLPs to be NLP models to be fair, accountable, and transparent models. Not only after deployment, but also before that. So when we're building the models, we want to make them accountable and transparent, and also fair to different categories of users. So all of them involve interpretability. And what does interpretable NLP involve? This is mainly about the ACL track interpretability and analysis of NLP models, but it's broader than that. And there's a black box NLP workshop, and there are some connections to FACCT, machine learning for health, and psycholinguistics, and learning theory and linguistic theory, and natural language processing plus society. and also machine learning for NLP track. And recently there are two tutorials and one course that discuss the relevant topics, but they're discussing very different topics. For example, the ACL tutorial talked about diagnostic classifiers and behavioral tests, and the EMNLP tutorial talked about the influence functions and understanding the data set. And there was relevance propagation, etc. We will cover all of these topics in this seminar series. And also the Stanford class is more on the deep learning side. They are focused on the algorithms. So there are some overlapping with interpretable NLP, but we are focusing more on the NLP side. We will cover these topics and many others, including the geometry of representations, diagnostic probes, behavioral testing, causal interpretations, the influence of data sets in interpretability and dialogues, and many others. But we're still developing the slide and the actual topics of this subsequent data sets and the subsequent talks. And we will meet on Tuesdays 9 to 10 Toronto time. And the information, including the reading list, is posted on this website link. Okay, great.